Aneta Wiśniewska, and I'm working at the Leibniz Institute for Astrophysics in Potsdam. And today I will be talking about the oscillation in the solar atmosphere and in a special case of C-class flare. Yeah, but first I want to tell you something about myself. I did my PhD on atmospheric seismology at the Freiburg University, and I was working at KISS at the time. Then I switched to some other physics department, and I was working as a postdoc on secondary radiation detector for medical treatments, and it was in Krakow at the Jagiellonian University. But then I decided to go back to the solar physics, so I got a position at the AIP, and my main duty is now ground-based observations at the Gregor and the VTT telescope. Okay, and because maybe not all of you are familiar with that, I will introduce you shortly helioseismology and what is the observed oscillation in the sun. Then I will try to introduce you a little bit to the seismology of the solar atmosphere and go through active regions, solar flares, and I will show you the results on the frequency distribution in active region during the flare event. And I will tell you what I would like to do then further. Okay, so helioseismology actually aims to estimate the origin of the solar pulsation, and the sun is an ideal object for seismic probing because of its proximity. And the helioseismology, actually the oscillations was discovered by Roger Lytton already in 1960s. He was just investigated the solar spectra, and he found out by the measurement of the Doppler shifts that the solar surface is pulsating, and they found the velocities around 15 centimeters per second. Then it was further explained in more detail by Ehrlich and independently by Leibacher and Stein, and they construct kind of more advanced power spectra of oscillations, which are shown here. And here you can see like the model full disk Dopplerogram, and this is actually done from the Gong data. And you can see that the most dominant oscillation is the 5-minute pulsation, and it has like a global nature on the sun, but still you can see here the solar rotation, so the Doppler shifts. Okay, I don't want to go too much to the theory, but basically the helioseismology based on the model of spherical symmetric perturbations, which are described by a spherical harmonic function, and oscillations are characterized by individual quantum numbers, which is n, l, and m, and you can see here on this very nice plot, which called power spectrum, observed distribution of oscillatory power. And you can see here that the most of the power is concentrated on so-called ridges. And if you want to imagine how the sun is oscillating, of course this oscillations is several million of modes. So I just prepared for you some kind of visualization. And what is important that each of the modes of the frequencies penetrate different depths of the sun. And so as you can see, these depths are depending on the frequency, and for the different modes this looks like differently. And okay, so this was the case if we would like to go inside the sun. Now the question is, what if we want to observe or probe the solar atmosphere? Is it possible? And the answer is yes, it is possible. Just the one difference is that we are not going inside the sun. We try to probe the oscillations which are propagating outside into the solar atmosphere. And basically, you saw already this cartoon before. So the solar atmosphere is very, very inhomogeneous, and especially when the sun is in its maximum. So we can observe at the different layers of the solar atmosphere using different spectral lines. We can observe different features. So, for instance, the sunspot at the level of the photosphere looks like we all know how does it look like. So it has like a penumbra, umbra, and the quiet sun in outside. But if you are looking higher up, this is actually measurement with the H alpha line. You can see already different features, and therefore we can probe the solar atmosphere at the different heights using various spectral lines. And of course, then if we will be having like a kind of cuts through the atmosphere, we can say something about the propagation of the waves, so how they are propagating towards higher layers. And what is important, that we are using basically the same Fourier approach, so the Fourier transformation, but for the smaller field of view, and we are measuring at the disk center to avoid this solar rotation effect. Yeah, so this is like the basics of the helioseismology. So basically, if we have a data set, we need to have the velocity signal of it, so the Doppler derived from the Doppler shift, and the Fourier transform of such a signal, which is located at the specific place and in time. If you transform this using a Fourier transform, you obtain the power spectrum of the velocity signal. Then you can investigate it further, constructing that this is the next equation representing the cross spectra of the same signal. However, what I would like to show you, if we do this for the different spectral line, we will obtain the different results, which is very, very interesting. And we see the difference in the power at the different height of the solar atmosphere. So the last one is H alpha. I will show you again. We are starting at the photospheric level. So you can see that these ridges are very nice visible. But when we are moving higher up, the power decreases. So I have done already such a research for power suppression in active regions, and I probed the quiet sun and compared these two active regions to the regular quiet sun, let's say. And we see, of course, the power suppression when we are observing active regions. It is obvious, and this is actually what we expected, and we can compare directly such a spectra because they were done with the same instrument, with the same cadence, and with the same filters. So they are like perfectly calibrated. And so we can compare in between them. However, I don't want to speak about that because I'm interested now in the flares. So we had measured also one flare. And it was a C-class flare, and as already you've heard already on this school about the magnetic reconnection, and that the flare are mainly consequence of the magnetic reconnection. So they arise high in a corona, but then part of the non-thermal electrons is moving downward to the solar chromosphere, and we can observe also the flares at the level of the solar chromosphere. Yeah, so as I said, we did the measurement of the solar chromosphere, and we had observed the flare at the time. I wanted to see how does it look oscillation on the level of the photosphere and the level of the chromosphere when we are talking about the flare. So here you can see the plots of the so-called power maps. They are based on the same Fourier transformation, but they are like in a 2 dimensions, so we can distinguish between different frequency bands. And this is a photospheric iron line, 6302 angstroms. So this is like, I don't know, maybe 200 kilometers above the so-called solar surface. Sorry. And to compare, we have a different spectral line for the same region. So we are now very high in a chromosphere already, and we can see the difference between these pictures. So basically, the difference is that the spatial power distribution in the level of the photosphere and the level of chromosphere is different. So we can observe more power in a flare region at the level of the chromosphere, and the less power at the same region in the level of the photosphere. However, it was done for the data which were taking 2 hours before the flare occurred in a corona. So this is like very interesting that we have already observed something here. So I plot already like the contours of the flare. This is like a post-flare loop, and these are the pores. So let's see what's happened if it was shortly after and in a prior of and in a prior of the flare. So we can see different maps, and here is of course a big difference. So we don't observe almost the power in a region of the solar photosphere is highly decreased, but instead of that we observe like everything. So the power, the waves are concentrated in the chromosphere. So we observe them in the H alpha. Yeah. So as you can see here, the almost all power is concentrated in the flare region and inside the post-flare loop. So here, whereas here there is nothing, almost nothing left, and in the surrounding of this region, at the level of the solar photosphere, we don't observe much power as well. Okay. And of course, I did this measurement for the multiple lines. So we have like a kind of cuts through the solar atmosphere. And actually, I had measured 9 lines, but only 7 of them was useful to do the investigation. And I chose like one frequency band to show you, because otherwise it would be too much. So you can see the difference before the flare occurred and shortly after. So you can see that here the most power is concentrated very high in the chromosphere, and you can also see the difference around 600 kilometers here. Here is not much visible, but still there are some differences. So we know that the power is like the waves are just propagating upwards. Okay, so now what I would like to do next is the seismology of the solar corona. However, this is very challenging, and I would like to use to that not only AIA data, but also the data which will be coming from the solar orbiter. However, this is very tricky, and therefore I don't want to present you the ideas how to do it, but in general, I would like to use the same methods which we're using for the chromosphere and the photosphere.
Thank you very much.
Yeah. Thank you.